Welcome back. In the last lecture, we have seen that if f n is a fair kernel, then f convolution of f n converges pointwise to f of x naught if f is continuous at x naught, and if f is continuous function, 2 pi periodic continuous function, then f convolution of f n of x converges to f of x uniformly. So, there are certain basic properties of the Fejer kernel enabled us to derive this result, and as an application we have seen that if we have f hat, then we can reconstruct our f trigonometric polynomial. They are dense uniformly in the space of continuous function, and very important result, if f hat is equal to g hat at every point of z, then f has to be equal to g. So, that is the uniqueness of the Fourier transform. So, now if we try to generalize the properties of the Fejer kernel what we had seen, let us see what happened. What do I mean by that? A family of kernels k n n equal to 1 to infinity. They are the 2 pi periodic functions on minus pi to pi is said to be a good kernel or an approximate identity if the following conditions are satisfied: 1 by 2 pi minus pi to pi k n x dx is equal to 1. Secondly, 1 by 2 pi minus pi to pi mod of k n of x dx is lesser equal to m for some constant m. This is for all n. And third, for every delta positive, integral mod of x greater than delta, greater or equal to delta mod k n x dx, this goes to 0 as n goes to infinity. If these three properties are satisfied by a sequence or a family of functions k n, then we say that family to be a good family or an approximate identity. Why it is an approximate identity? Because we have seen that under convolution C 0 1, if I take two functions and convolve them, they have they are continuous, and then one would like to ask, does it have an identity? And it will never have an identity, because the Fourier transform vanishes to 0. So, but that is how here what we are approximating with a family K n, in particular f n f by a convolution. So, exactly by following the idea of the proof of Fejer theorem, we can get this. Let f is a 2 pi periodic Riemann integrable function. If f is continuous at x naught, then f convolution of k n of x naught, this converges to f of x naught. Moreover, if f is uniform, if f is continuous on minus pi to pi, then the convergence because for every point in x by the previous statement, this is going to this f convolution of k n of x converges to f of x for all x in minus pi to pi. But if we are dealing with a continuous function, then we will get that the convergence is uniform. Okay, the proof is basically exactly the same as that of the Fejer's theorem. So, it is not a very bad idea to repeat the proof. Let f be continuous at x naught, then we want to show f convolution of k n of x naught minus f of x naught. This is 1 by 2 pi f of x minus of y k n of y dy. Now, minus of f of x naught. So, now what I can do is that multiply 2 pi and divide by pi, 1 by 2 pi if I take it out, this is minus pi to pi k n of y dy. So, this is less or equal to, like in the Fejer theorem, we can break this minus mod of f of x minus of y. This is x naught minus of y minus of f of x naught into mod k n y. Here we do not know whether k n is a positive function or not, but that is not going to matter. This is minus pi to pi. And again by the continuity of the f, for every epsilon positive there exists a delta greater than 0, such that mod of y less than delta will imply less than epsilon. So, now with this delta we take this is equal to 1 by 2 pi and we break the integral into mod y less than delta plus mod y greater or equal to delta, and then within the integral, that is there is mod f of x naught minus y minus of f of x naught mod k n of y. Okay. So, in the first integral, the continuity of f is going to give us the smallness, and in the second integral we will pull out the bound for f. So, that will be 2 times the supremum of mod of f of x will come out, and f is a Riemann integrable function and is bounded, and then we are left with. So, this is less or equal to some epsilon into minus pi to pi mod of k n of y dy, that is the first integral, and the second integral is going to be less or equal to twice the bound of f Now, while in the choice of delta, we can always take that, and this is less or equal to m, that is what is our assumption of a good kernel is. So, we can make it 2 by m. Now, here this is less than epsilon, and this one second term goes to 0 as n becomes large. Thus, f convolution of k n at x naught converges to f of x naught. Exactly the same proof, it is just a bookkeeping of the proof of Fejer kernel. And if it is a continuous, if f is a continuous function, here this existence of delta may not depend on any x naught. Therefore, what we are going to get is that this is a uniform continuous function. So, hence the convergence is going to be uniform. Okay. So, that is so now what are the other examples of good kernel? Let us take V n of x is equal to 2 f 2 n minus of f n. So, now what is interesting about this family? Now, for each n, if we look at, recall that f n hat is equal to 1 minus mod n by n if mod n is less or equal to n and 0 otherwise. Therefore, V n hat is going to be, let us draw the diagram. Here I have n, here I have 2 n, here minus of n and minus of 2 n. So, V n hat at n by the linearity of the Fourier transform, we have twice f 2 n hat at n minus f n hat at n. Now, when if our small n is lying between minus of n to n, then both f 2 n hat is also 1 minus mod n by 2 n, right. So, therefore, 2 n hat, this is going to be 1 minus mod n by 2 n if mod n is less or equal to 2 n in this. So, now if mod n is less than n, this is mod n by 2 n. So, now V n hat is equal to 2 times 1 minus mod n by 2 n minus f n hat is 1 minus mod n by n. Now, if you take this, then this is 2 minus 1, which is going to be 1 here, this entire. Now, between n and after 2 n, f 2 n hat is 0 and also f n hat is 0, therefore, that difference is 0. So, now let me do change of color. This is 1 here and this is 0 on this side. Now, in this side between n and 2 n, f n hat is 0. So, this is nothing but 2 times f 2 n hat. So, therefore, at a 2 n this is 0. So, this is something like that. So, the Fourier transform of this V n is going to look like this, and this is very useful. At certain stage we will be using this kernel instead of the Fejer kernel. So, this is one example, another example of a good kernel. So, now some another important example. Remember that in this example we will see that when we are talking about the good kernel here, we have taken it is a family to be a countable family, but not necessarily that we need to have a countable family. So, now define P r theta, this is equal to summation over n equal to minus infinity to infinity r to the power mod n e to the power I n theta, where 0 is lesser equal to r is less than 1. So, this you can see that if I consider a unit disk, then at each point can in the polar coordinate can be represented by r theta, and so this you can think of that this is a function which is defined on the open unit disk. Now, let us see, and this is because r is less than 1. So, this infinite series converges. So, we do not have any problem with that. Now, 1 over 2 pi minus pi to pi p r theta d theta, this is equal to 1, because this is absolutely summable series, we can pull the sum out of the integral and varies over z, and r to the power mod n is independent of theta, can come out, we are left with minus pi to pi e to the power I n theta d theta. And we know that this integral is going to survive only when n is equal to 0, and for other values of n this integral will vanish. So, this becomes nothing but 1. Okay, the first property of the good kernel is satisfied, even though here this is true for all r. Now, next condition for good kernel to be we need to have the control over the integral of the modulus of that function. In the case of Fejer kernel, we saw that the Fejer kernel is a non-negative function, therefore, we did not have any problem, and then we impose the condition that the modulus of the kernel is lesser equal to some constant m for every n. Then so, now what is this? So, let me call it as a lemma P r theta, this is equal to 1 minus of r square by 1 minus 2 r cos theta plus r square for r belongs to 0 and 1. So, as you can see that obviously, if r is less than 1, then this is going to be, and cos theta varies between minus 1 to 1. So, therefore, we get that P r theta is positive as a simple consequence of this lemma. If we prove this identity, then we can prove that 1 over 2 pi integral minus pi to pi mod P r theta d theta is going to be equal to 1. So, the proof of this is simple. P is just the complex number, complex algebra. So, this is, I can write this as minus infinity to minus of 1 r to the power mod n e to the power I n theta plus summation over n equal to 1 to infinity r to the power n e to the power I n theta, and 0 term is going to be 1, okay, n equal to 0. Now, this becomes 1 to infinity r to the power minus of n e to the power this is minus I n theta, and this is minus n mod. So, which means is equal to n. We can replace this by n plus summation over n equal to 1 to infinity r to the power n e to the power I n theta plus 1. Now, r is a positive non-negative number which is strictly less than 1. Therefore, both the series are geometric series and we can sum them. So, now what it is missing over n equal to 0 term. So, therefore, if I write this as this is 1 minus r to the power r into e to the power minus of I theta, and then minus of 1 plus 1 by 1 minus r e to the power I theta, then this is minus of 1 plus 1, because to add and subtract the 0th term. So, this is equal to and this is minus of 1. So, this is equal to, if we do simple addition, then what we have got, this is 1 and minus r e to the power I theta, then minus r e to the power minus of I theta. So, that is going to be 2 r cos theta, and this into this is plus r square, and then this is 1 minus r e to the power I theta plus 1 minus r e to the power minus of I theta, and then this is then minus of 1 minus r e to the power I theta, then minus r e to the power minus of I theta, and then this is minus plus r square. This is nothing but 1 minus of r square divided by 1 minus 2 r cos theta plus r square. So, the second property of P r, this family, to be a good kernel is also satisfied. So, this basically will imply 1 over 2 pi minus pi to pi mod of P r theta d theta. This is equal to 1 by 2 pi minus pi to pi P r theta d theta, and this is a because this is a non-negative quantity. So, this is equal to 1. So, this is the second condition what we have got. Now, the most important part is also the third condition. So, the third condition says that away from the origin if n goes to infinity, then this integral of k n has to be small, it goes to 0. Here instead of n goes to infinity, what we would like to see that what happens when r goes to 1. So, for delta positive limit r goes to 1 minus 1 by minus pi to pi, no, mod theta greater or equal to delta p r theta d theta, this will be 0. Okay. So, let us see. One, as we know, the numerator is 1 minus r square. So, when r goes to 1, the numerator is going to 0. Now, the denominator, we would like to see that when r goes to 1, it should not, if we can say that it has an upper bound, then we are done. So, 1 minus 2 r cos theta plus r square, this is equal to 1 minus r whole square, I am adding minus 2 r plus 2 r, then plus 2 r if I am taking it common, 1 minus cos theta. So, 1 minus cos theta, this is going to be 1 minus of r whole square plus 4 r sin square theta by 2. Now, in this region minus pi to pi, sin theta mod sin square theta will go something like this. Now, theta is here. So, now if mod theta is greater than theta and less than pi minus delta, this is delta, then obviously sin square theta is going to be greater than. So, this is 1 minus, and if theta lies between pi minus theta greater than delta greater than delta, this is 1 minus of r square plus 4 r sin square delta by 2, and if r goes to 1, then this thing goes to then 1 over this. So, p r theta is less or equal to 1 minus of r square by 1 minus of r square plus 4 r sin square delta by 2. Now, this goes to 0, as r goes to 1, this is 0, this is 4 sin square delta by 2, which is a positive number, and 1 minus r square, it goes to 0. So, the third condition for this family to be a good kernel is there, good kernel. So, now this is a family which is not a countable family, but still it satisfies all the properties to be a good kernel. Thank you.